Okay, we're going on, and our next speaker is Nana Galaski from Simplan, Germany, who will tell us about the agent-based model to design and support e-mobility transformation for municipal vehicle fleets. So, welcome, Nadia, and here you are.
Thanks, Daria. Thank you for joining me today. My name is Nadia Galaska, and today I would like to tell you more about our project in using an agent-based simulation model to support the e-mobility transformation for municipal vehicle fleets. I work at the Simplan in Germany. First, I would like to give you a short introduction about Simplan and what do we do as a company. Simplan is based in Hanau in Germany. Simplan is a cross-sector full-range supplier with regards to simulation and optimization. So we basically do everything in terms of simulation. Our portfolio consists of 4 different categories. Our focus is in simulation consulting. We develop models for our clients. We do studies. We also develop libraries for our clients. And we also offer our clients a solution in regards to optimization and integration. And we also an official distributor for AnyLogic. We also offer the trainings in using the AnyLogic. Our client comes from a broad sectors. So we have a classical automotive industry and supplier to healthcare simulation, business process or transformation. And we are also involved in several research projects with a focus on simulation, logistic, and digital twin, basically with simulation and also with the optimization. One of the research projects is the SimCityNet, and today I would like to tell you more about this. So in the project SimCityNet, we want to build a digital twin for the e-mobility transformation in the municipal vehicle fleets. What were the motivations? First of all, the climate effects is a hot topic in Germany. And we think that when we change large vehicles such as buses or trucks to zero emission vehicles, then we can significantly reduce the air pollution and overall improve the quality of life, especially in urban cities. Also, the economical aspect is that with the surging fuel price in the future, the cost of a lifetime might benefit of the electric vehicle fleets. And last but not least, we also have the Clean Vehicle Directive in Germany, which basically states that by 2025, 45% of buses purchases must be of low emission, and half of them must be of zero emission. And this ratio will grow over the next 5 to 10 years from now on. So that means that we are not talking about 1 or 2 vehicles in the fleet, but maybe 30, 40, or 50 or more vehicles of the fleet. So that's why we need to develop a simulation model in order to be able to assess the impact of the alternative vehicle mixes on a global scale. So we want to consider the battery electric vehicle and also the fuel cell electric vehicle. And we want to assess, for example, the impact of number of required vehicles. So do we need a larger fleet? Do we need to keep the diesel-powered vehicles as backup? Also on the infrastructure, so what kind of infrastructure do we need? How much power do we realistically need? And also the impact on the operational consequences. For example, can we keep the existing schedules or can we optimize this optically? or do we need to change the schedules to suit the new electric vehicles? So, and our use cases is we have two use cases. First, we have the public buses in Hanau, which is the Hanauer Straßenbahn in Hanau. They have a fleet consisting of 65 buses. And our second use cases is the waste collection operator in Hanau with a fleet of about 16 garbage collection trucks. And we want to assess the impact. What happens if we electrify the fleet? So if we change the fleet from currently diesel-powered vehicle to battery electric vehicle or fuel cell vehicle. Basically, what were the challenges? First of all, is the range limitation. Currently, the diesel fueled bus, for example, has a range for about 500 kilometers. And with the battery electric vehicles, we only have about half of the range that is available. And additionally, we also need to consider seasonal changes in temperatures. For example, buses need to be heated in winter. This means that the range available will be reduced significantly due to the heating. So that means that the current tour might not be feasible anymore, and we need to split the tour in order to be able to offer the same service level as currently is. And that means that perhaps we need additional vehicles in order to be able to do the tour. The second challenge was the charging processes. So we made an assumption of a linear charging process. It will not capture the full complexity of the issue, as the charging power of a vehicle depends on several factors, such as what is the current state of charge of the vehicle, what is the charge power available in the charging compound, and perhaps also how many vehicles are currently charging at the same time. Now, let me give you an overview of the model and the workflow as well. So first, we have the input data that is required for the model. For example, we have the vehicle configuration data, which contains the vehicle model that we want to consider, the range, consumption of each vehicle type, and also the charge speed over the state of charge. Also, we have operational data, schedule data, and also the location data. For example, where are the bus stops located, or where the waste container are located. So this data is stored in Excel or in external database, and it will be fed into AnyLogic. In our model in AnyLogic, we also have a user interface for configuring this scenario. And then we can run the simulation model in AnyLogic, and then we can gather the results and push the result into database and use our proprietary tool Simsys to evaluate the core KPIs. In the model itself, we have different types of agents. So we model each vehicle as an agent, a facility agent, and we also have transport management and charging management to manage the tour and the charging process globally. For the charging management itself, each vehicle will have its own charging management, and the charge speed of our SoC for each vehicle is modeled. And once a vehicle needs to be charged, it will use using this state chart, it will trigger the charging and request the charging power from the global charging management. And the global charging management will manage the power consumption within the power constraints of the charging infrastructure and distribute the power accordingly based on, for example, how many buses are currently charging and how many buses need to be charged. So In short, we end up implementing a load balancer for the charging power, and we expect that this kind of feature will be commonly used in the future as the demand for electric vehicle grows. And last but not least, we also develop heuristics in Java and embed them as a library in AnyLogic. For example, for location mapping, for vehicle scheduling, and also for the arc routing problem. And this was one of the unexpected highlights that we face in during the modeling. So unlike buses, which is pretty much straightforward, so a bus travels from one stop to the next stop. But for the waste collection tour, we do not have any predetermined sequence. So we have a network of streets and junction, and we have the location data of our waste container. So we needed to implement a route search algorithm to determine the sequence of the waste collection tour and need to consider several restrictions. For example, on some streets, the waste truck can collect the waste container from both sides at the same time, but on several streets, for example, if the street is very large, then the truck can only collect a waste container from just from one side only. So that means we need for our as a databases for our route search algorithm, we need to consider the distance, the amount of waste volume, and also the operability separately. And also another chance was one-way street. So if there's any one-way street, then we have to make sure that waste container from both sides need to be collected, because the truck can only drive from one side, from one junction to the next, and that's why we need to detect whether a street is a one-way street or not. Next one is that waste collection truck is a large vehicle, and you don't want this kind of vehicles to make a U-turn at a junction, because then it will block any incoming traffic. So that means that we need to make sure that a U-turn is avoided in our algorithm. Also, last but not least, in housing area, for example, we have waste containers that are not directly located on the street. So that means we need to determine the closest section of accessible road that can be used to collect the waste container. So let me give you an impression of the model. So first, I will show you the how to do the configuration in the model, and then I will show you an impression of the model run. So in the UI in AnyLogic, a user can configure the model and then select, for example, what kind of scenario they want to run and what kind of vehicle types that they want to consider. For example, here you can click on the battery electric and fuel cell. And then in the next step, you can configure the fleet configuration. So you can select any vehicle model that read from the data, and then enter the number of vehicle that you want to use in the simulation. In case you have battery electric vehicle, you can also consider the battery aging as well. Then you need to define the charging infrastructure. So what's the location, number of charging stations, power, and also the SOC limit to charge. The same goes for the fuel cell electric vehicle. Here you can also define the charging infrastructure as well. And for the scheduling, you can choose to use the current data, or you can choose to the algorithm to create a new tour planning, or to just modify the current planning data. Last but not least, you can select to consider school bus line. or also consider the temperature effect, such as the additional consumption in case the temperature goes in a specific range. And then you can choose to export the data to Excel or to a database. Here, for example, you can create a new database table or open database table. And then once you press start, and the model will load the data from the database, and then we'll start the simulation using the current data. So next, I fast forward the video for a second. So now we have 6:30 in the morning on Monday. As you can see, several buses are running. We have here we can select to show the different energy type or the range and also the state of charge. So then you can know which bus are currently running where. If you click on a vehicle, for example, you can see the current stops that the bus needs to serve. And here, fast forward a couple hours later, we have a rush hour and we have a great number of buses running in the city. And here we also implement the overview of the KPI here, for example, that you can see the current state of each bus in the simulation. So next one, I will also give you an impression of the model for the waste collection tour. So the model configuration is basically pretty much or less similar to the bus model. Here you also select the scenario and you also select the different kind of vehicle that you want to consider. And for the model run itself, here you can see the also the same map of the city of Hanau, and here you can see where the waste container are located across the city. So here you can the model can give you an overview on where the waste container are located. You can select different weekday or different week to have an impression of where the container are located, and you can also see the different kind of waste type that needs to be collected by different type of vehicle. So here we have residual waste, paper waste, packaging waste, and organic waste. And if you click on a vehicle, you can see the same as before. You can here also visualize the energy type, the current range, and the state of charge. And here you can also see which waste container it should be collected by the vehicle itself. And once a container is picked up by a truck, then it will be removed from the visualization. So during the simulation run, you get the visualization on the progress of the waste collection tour. So it's kind of like a Pac-Man model where, yeah. And once the maximum load of the vehicle has been reached, then it will go to a disposal facility, unload the pickup waste, and then continue the tour as well. Here, similar as to the other model, you will also have several kind of visualization of the current state or of the fleet as well. So yeah, and then once all of the waste container are once the tour is finished, then the waste truck will go back to the depot, and then we can start charging process. So yeah, as for the results, we use the visualization in AnyLogic to visualize the current state of the simulation run. For example, here, as you saw previously, that you can see the current state for each vehicle, but you can also see that the duration, the distance, or also the required energy amount. And as for the detailed results, so we gather detailed data from the results, and then we export them to an Excel or SQLite database, and then we can use the evaluation tool to compare the scenarios from different runs. And here, for example, you can get an impression. So what is the number of required vehicles based on the vehicle type. Here, for example, that in case of battery electric vehicle, the temperature effect has a significantly impact on the required number of vehicles, as in colder months, you will need a greater number of vehicles compared to the warmer months. Another result is that we can make an estimation, so how much power for the infrastructure that we need. And so we can also analyze what happens if we, for example, have a limited charging infrastructure, for example, only a limited number of charging station or a limited power in total, and we can analyze the impact on the vehicle scheduling itself and the available range. So to sum it up, yeah, our conclusion is that simulation model is a necessary means to make a realistic forecast on the requirement for the large-scale application of an electric vehicle fleet. And only by using the simulation models, we can assess the impact in the daily operation. This kind of modeling approach is also generic. So that means that we can apply the same modeling approach to another region or other types of fleet. Possible for development from our side is, for example, we can consider or we should consider perhaps opportunity charging instead of overnight charging. And also, for example, in rural areas where the bus don't run on a exact schedule, we can perhaps consider an on-demand tours and react to real-time customer requirements. Finally, our vision is that this simulation model should be able to act as a digital twin and to be used in day-to-day operation, and that's the direction that we want to develop ourselves into, and that's the direction that we are going to. So that's all from my side. Thank you for your attention, and I see that there's some questions.
Yes, we have a couple of interesting questions, so I suggest to go through them and look at them and answer.
Yeah. Okay. So I will go from the top. I have a question from Stuart. Where we so the question was, were we looking at alternatives to direct electric vehicle charging, so with battery swap station? Well, no, that was not the requirement for the project. So that here, well, because the vehicles are going to be used in day-to-day operation, and then that's why we want to look into that charging process on electric vehicle as well. Okay, and there's a question about the input data as well with loading data. Yeah, so we for the data we use the we load the data into the internal database of AnyLogic, and basically it's possible to connect the internal database of AnyLogic to a MySQL database. So that's why we want to have the flexibility, or for example, if our client do not have the data in a database but only in Excel, that we want to be able to consider this as well.
Yeah, I think we have time for one or two last questions, so
Okay.
we can go further.
Yeah. Okay. So let's go through the question. Yeah. So the effect on the air temperature on the battery discharge. Yes, we consider that as well. So we model that as an additional consumption in this term. So that means that in case of colder months, that we added an additional consumption based on the data that we have, and then consider them in as well. And as the project itself, the project was well, it was a research project. It went for 3 years, and we had an analysis phase at the beginning and developed the concept. And for the modeling itself, I think it was done in the last year of the project phase. So
we can take the last one question before we go on to the next speaker.
Okay. Okay, yeah, I think that's one interesting question. The location of the charging point, we didn't consider the well, we at the moment all of the charging process are done in the depot. So that means that we only have a fixed location of the charging infrastructure. Yeah, but I think that might be an interesting option to further develop the model. That means that if you don't have only one fixed location but several different locations, and then use an optimization to find out which location is the optimal one to charge the vehicle. I think that will be interesting as well.
Okay, thank you very much. Thank you very much for your great presentation. So
Thank you as well.
I'm sure that people have some more questions, but unfortunately we don't have time to revise all of them. So I would like to ask you to send it once again to Nadia directly in the private messages. And thank you once again, Nadia, for your great presentation. Thank you very much.
Thank you. Bye.
Bye.